continue our lessons on three-dimensional coordinate system. By this time, we take a look at functions of several variables, and we're looking at the domain of the functions of several variables, and then we look at how to sketch them. So the function y of f of x is a function of a single variable because the function depends on a single independent variable, x. Functions which depends on two or more independent variables are said to be functions of several variables. So for example, u of xy equals x squared plus y squared is a function of two variables. V of xy is equals to this, it's a function of three variables. Now, we define a function of two variables as a rule that assigns to each other pair of real numbers xy in the set D a unique real number denoted by f. So when you put in this, you get a real number unique denoted by f of xy. The set D is actually the domain of f, and its range is the set of values that f takes on. So that's how you get the range. The domain in this case is an ordered pair which is defined for the function f. So let's take this example. We want to determine the domain of each of the following functions and sketch them. So you take this one. You know that you need your basic knowledge in functions. The square root of a number can never be negative. It can be 0. So we say that x plus y should be greater than or equal to 0. We can say therefore y is greater than or equal to negative x. So that is the domain. So we can say that the domain is x, y, such that x plus y is greater than or equal to 0. Or we can say that y is greater than or equal to negative 1. And this is the domain. So we want to sketch this. So if we draw our x and y as this, so this x, this is y. We are saying x is greater than negative x, but the line y equals negative x is this line passing through the origin. And if you want, where we sum x and y, you get negative. You know that it is this area. So this region is y greater than or equals to negative x. So all this region. So that's a sketch. Now let's look at this one. Here, they are individual components. So you have to treat them as such. So the domain is such that x should be greater than or equal to 0 and y should be greater than or equal to 0. So we say that the domain is x, y, such that x is greater than or equal to 0 and y is also greater than or equal to 0. The two must hold. So if I want to sketch this, x greater than or equal to 0 is everywhere here. It's not part. So everywhere here. Then y greater than or equal to 0 is also everywhere here. And you can see that this portion here is double shaded. So that is the side that satisfies this function. Okay, so let's look at this example 2. We are to find the domain of this function. You know, this is a lim function and it's also in an absolute value. So you know you cannot find the lim function of a negative number, but because of this absolute value, if the number is negative, the absolute value will take it to positive. The only thing that we want to restrict ourselves from is that the 9 minus x squared minus 9y squared can never be 0. So the domain is in such a way that 9 minus x squared minus 9y squared can never be equal to 0. And in that case, we are saying that x squared plus 9y squared can never be equal to 9. And this is a domain. So we are saying that the domain is all the regions xy such that x squared plus 9y squared is never equal to 9. And that is the domain. So if you are to sketch this, you know that this is an ellipse that you are going to get. And so far as anything here within this one doesn't defile this condition, it becomes part of the domain of this set. Now we will now take a look at graphs of functions of several variables. So in fact, we have limitation as to the number of dependent variable functions in which a graphs can be sketched without the use of computers. And those limitations are limited to functions of two variables or functions of a single variable. But here we are dealing with some functions of several variables, and we are limited to functions of two variables. For example, GeoGebra can sketch graphs of functions of two variables, but three or more is not possible. So to sketch a graph of function of three or more variables, you need to special software and sometimes computers with higher graphics model. So we're going to, in this lesson, we're going to limit ourselves to functions of two variables. So let's look at this function. We want to sketch the graph of the function f of x, y equals 6 minus 3x minus 2y. In both cases, we are going to look at the GeoGebra and then the regular sketch. So let's look at the sketch here. We know when you write functions like this, the f of x, y is actually can be represented by z, because we have the three-dimensional coordinate system as this is the x, y, and z axis. So this is the x, this is y, and this is z axis. So we can write the equation as z equals to 6 minus 3x minus 2y. So what we do is that we find the intercepts on each axis. On the x-axis, y and z are all 0. So here means we are going to get 0 to be equal to 6 minus 3x, and therefore 3x equal to 6, and x is 2. So the point there is 2, 0, 0. Then for the y-axis, x and z are both 0, so we are going to be left with 6 minus 2y equal to 0, and we have 2y equal to 6, and therefore y is 3, and then you're going to have the point at 0, 3, 0. And on the z axis, x and y are both 0, so you are going to be left with z equal to 6, and therefore the point there becomes 0, 0, 6. So this is the point that we plot on the axis. So if you pick the point 0, 2, 0, 0, so it means that x equal to 2 comes somewhere here. And then if you pick the point 0, 3, 0, y equal to 3 comes here. And then 0, 0, 6, z equal to 6 comes here. So we join this with a straight line. So the surface here, the whole surface here is a plane, and it goes beyond this because the plane we are sketching manually, so we have limitations. We will look at GeoGebra. Okay, so this is a GeoGebra, and it's a 2D window, but we need a 3D window. To get a 3D window, we go to the view and 3D graphics. When I click on that, we are going to have the 3D window here. We don't want the 2D, so we can close it and then get a full 3D window. I just want to change some few properties here. The graphic background there, I'll click on this smaller arrow at the 3D graphics and then remove the dark surface and maybe put the grid there. And the red is the x-axis, that is the green is the y-axis, and the blue is the z-axis. So we can type the function straight away, and then the graph will be drawn. So if I type the function straight away, let me delete this. I'm going to have f of x comma y equal to 6 minus 3x minus 2y. Press enter, and that is the surface that we have here. So if I reduce it a little bit, you realize that the thing passed through all the 3 points. So you are going to draw the points and see where the points that we just plotted manually are. So the first point was 2, 0, 0. You can see that's the point A, and that's what we are seeing here if I put it here. Then the second point was 0, 3, 0. So that is this point we are seeing over here, and the third point is 006, 0.6. So these are 3 points that we just plot, and in manually what we did was we joined these 3 points. So if I pick this polygon 2 and click here, and there, and there, this is a point that we joined, but it goes beyond. So you can see that that is exactly at the surface there, but it goes beyond that. But manually we have limitations in the sketching. Okay, so let's look at it. We look at the domain of the function and sketch the function. Domain, we know that this one shouldn't be 0. Any value here shouldn't be less than 0. So we have 1 minus x squared minus y squared should be greater than or equal to 0. Therefore, you're going to have x squared plus y squared should be less than or equal to 1. And that's the domain. So we say the domain is all points on the plane such that x squared plus y is less than or equal to 1. Now to sketch, we do the same thing. We let z to be equal to 1 minus x squared minus y squared. So in the x-axis, our y and z are both 0. So you're going to have 1 minus x squared equal to 0. X squared is 1. Therefore, x is plus or minus 1. So the point become 1, 0, 0, and then negative 1, 0, 0. Now on the y-axis, x and z are both 0. So you are going to have square root of this is supposed to be square root. You're going to have square root of 0 to be equal to square root of 1 minus y squared. Therefore 1 minus y squared is equal to 0. Y squared is 1 and y is plus or minus 1. So the points are 0, 1, 0, and then 0, negative 1, 0. Then the last one on the z-axis, x and y are all equal to 0. So you're going to get z to be equal to square root of 1. And the square root of 1, we are looking at only the positive side because there's no plus or minus here, so it's only positive. So that will be 1. So you're going to have 0, 0, 1. So these are the points. So we sketch our axis. This is x, this is y, this is z. So x is 1, 0, 0. So if 1 is here, positive 1 is here, negative 1 will go somewhere here. So this is negative 1. And then y2, positive 1 will be here, and negative 1 will go here. But the z have only positive 1. So that means that this one, if you look at this, the base is a circle of radius 1 and have a height there. So this is a half of a sphere. Let's go to GeoGebra and see how it gives to us. So this is the function. This is a GeoGebra with 3 dimensions. So let's just type the function f of x comma y equal to the square root of GeoGebra. You type a sqrt 1 minus x raised to the power 2 minus y raised to the power 2. So we see, because we took only the positive part of the z, we have only the upper part here, and then if we turn around, you see that is the graph that we have. It's a half of a sphere, and the points are all that you can see here is 1, negative 1, positive 1, and so on. We want to take a look at level curves. Now, level curves of a function of 2 variables are the curves with the equation f of xy equal to k, where k is a constant and is in the range of f. A level curve is a set of all points in the domain of f at which f takes on a given value k. In other words, it shows where the graph of f has a height k. But the typical real-life application of a level curve is a contour line that we use in denoting a mountain and the height. So you can see that sometimes we draw this to indicate the height of a mountain. The social study, you do this, a lot of them there. And then to indicate a mountain on the graph, and we tell you, we indicate the height here, maybe this is 100 meters above sea level, this is 200 meters above sea level, this is 300 meters above sea level, and so on. So we use it to indicate a mountain of a certain height. So if you cut through the mountain, that gives the level curve. So these curves here are the one we illustrated, and that is what we call the level curve. We will use GeoGebra to illustrate some few examples. So we start with this example. Sketch the level curve of the function 6 minus 3x minus 2y for the values k equals -6, 0, 6, and 12. So we are going to use GeoGebra. Let's look at it. Okay, so let's look at the GeoGebra. In this case, you are going to use the 2D instead of the 3D because you are going to take a look at the level curves on the platform. Okay, so we first start by creating a slider. So we put a slider here, and we are going to use integers, so a number, but you are going to start from -6 and ends at 12. If we check our k, the k values were -6, 0, 6, 12. So we are going to do an increment of 6. So that is our k. So I'm changing the a to k, and then I click OK. Then you are going to type the equation 6 minus 3x minus 2y equal to k. So you can see that we have one of the lines here with k equal to 1. So as you move, you can see that I'm having all the lines. So I want to draw all the possible lines. So I'm going to ask you to trace this line and animate this. And you can see that I have all the lines here. So there's a line k12. This one is k equal to 6. This is k equal to 0. And this is k equal to -6. So that's the level curve for this function. Let's look at also another example. We asked to sketch the level curves of the function g of xy equal to square root of 9 minus x squared minus y squared for k equal to 1, 2, and 3. So this one too, you go to GeoGebra and look at how it works. In this example, we have f of xy equal to square root of 9 minus x squared minus y squared. And we set that one to be equal to k, so you are going to have it as k equal to square root of 9 minus x squared minus z squared. Now what we do here is that we square both sides and make it 9 minus x squared minus k squared minus y squared equal to k squared. So that's what we type. But first we are going to set the slider as usual, and you're going to take an integer starting from 1 to 3. That's the maximum and the step size of 1. So our k here is 1, and we click OK. So we are going to see that this is 9 minus x raised to the power 2 minus y raised to the power 2 equal to k raised to the power 2. And you can see that this one has given us a circle of radius 8. So as you move on, the circle gets smaller into a dot. So let me trace this one and then animate this one. So you can see that as k changes, we have the various animation changes. So that is a level curve for this, because it's a circle of varying radius.